This video is about the roots of polynomials, which are the values at which a polynomial equals 0. So for a polynomial of even degree, how many roots does that polynomial have? Well, the possibilities range in between 0 and the degree of the polynomial. So that can be anywhere between 0 and its degree, any integer value. For odd, they have a minimum of 1, so there's at least one case where an odd degree polynomial is going to equal 0, and the maximum possible number is, again, the degree of the polynomial. All right, so what are these actually going to be for some specific cases? So if we have f of x equals some real number a0, so that's a zero-order polynomial if a0 is not equal to 0. So that has 0 roots if a0 is not equal to 0, because it's not 0 for all real values. So of degree 0, that's an even number. So we have 0 is less than n roots, which is less than 0. So the number of roots has to be 0. And that makes sense because the function is always something which isn't 0. And what if a0 is 0? Well, if a0 is 0, then we defined in the previous video that its degree is minus infinity. So I guess I should say, in principle, to be more exact, we could say the absolute value of the degree here. Because the degree is positive for all cases except for this special case of f of x equals 0. So in that case, it's 0 at all real numbers. So every real number is a root, and so there are an infinite number of roots if f of x equals 0. All right, so that has an infinite number of solutions, and all real numbers are an appropriate solution. All right, what if we have f of x equals a1x plus a0? So it's a first-order polynomial, which has some zero-order coefficient and some first-order coefficient to it. So that is going to have one root, because the degree is 1. 1 is less than or equal to n, which is less than or equal to 1. So there's going to be one root, and that is going to be at x equals minus a0 over a1. So just as we're taught to solve polynomial equations, 0 equals a1x plus a0, subtract a0 to the other side, negative a0 equals a1x, divide both sides by a1, x equals negative a0 over a1. Okay, what if we have a second-order polynomial, f of x equals a2x squared plus a1x plus a0? All right, how many roots does that have? That's going to have somewhere between 0 and 2 roots. So second-order polynomial, 0 is less than n, which is less than 2. So it can have all possibilities up from 0 to 2. So what are those possibilities? That is determined by our old friend, the quadratic formula. Now you're probably used to seeing this in terms of ax squared plus bx plus c, but we can write it out in terms of these coefficients as well. Whichever way works best for you is what you should use. So we have minus a1 minus b plus or minus square root of b squared minus 4ac, a1 squared minus 4a2 a0 over 2a2 over 2a in the traditional formula. Okay, so this is always going to give us two solutions, but they're not always going to be, well, it's always either going to give us two or one solution. If this value inside what's called the discriminant here is 0, then we're going to get one solution. But there will either be one or two solutions, but they won't always be real. So you can see here that we have a minus sign in here. So if 4ac is, or 4a2a0 is greater than a1 squared, then this is going to be negative, and this is going to give us an imaginary component. So these roots here could be complex. So how do we deal with this? So we have our real roots for second order. So we have 0 if 4a2a0 is greater than a1 squared. That would make this term negative, and make a square root of a negative number is a complex number. It has an imaginary component to it. All right, we have 1 if 4a2a1 equals a1 squared. If these terms are equal, then this square root is a square root of 0, and plus or minus 0 is still 0. So we'd have minus a1 over 2a2 if this value in the square root is 0. And then we have 2 if 4a2a1 is less than a1 squared. So then we'd have this number is bigger than this number, so we get a positive number on the inside. Take the square root of that, you get a minus 1 minus a1 plus or minus a number divided by 2a2. And you would get two distinct values from the plus minus. Okay, so then what do we do for beyond second order? So there are complicated but analytic meaning exact solutions, formulas for degree 3 and 4. So if you want to find the exact roots of a third order or a fourth order polynomial, which you can't factor out to either a second or first order, if you want to figure out those, if you want the analytic solutions for those exist and you can look them up. They get much more involved than this, and the fourth order one is quite involved, to say the least. So those exist, but beyond that, fifth order and beyond, we don't have exact formula for those analytically. So we typically solve those numerically. Numerically meaning solve it with some approximate method until you've decreased the error to some satisfyingly small value. So it depends on how accurately you want the number, but you can get it to kind of an arbitrary precision that you prefer. So we would solve this numerically for order 5 and beyond. Those might be some numerical methods like Newton-Raphson you might have heard of, or other numerical methods. This doesn't come up a lot in physical chemistry. Typically you're concerned with roots of second order, first order, zero order. So this doesn't come up a lot, but you may come across it once or twice on a homework set or something, depending on how hardcore your professor is with the math. But generally, knowing how to solve second order and first order and just in general factoring polynomials to get to their roots will serve you pretty well as far as things go for PChem.